measured in caloric. To some degree, to some degree. Let me just fix something here with the screen because yes. So the nature of heat, right? I mean, we have heard about heat in many aspects of our lives. Do we really know what heat is? Can somebody tell me what they think heat is? Hmm?
Heat's like a form of energy.
Yeah, heat is a form of energy. But what you're going to come to realize, thank you, Haley, it's a form of energy. What you're going to come to realize is that prior to us understanding that heat was energy, different scientists would have made certain suggestions as to what heat was described as, right? And so for this particular lesson, these are the objectives, the main objectives that we want to look at is to differentiate between the caloric and kinetic theory of heat as they exist, as they existed rather in the 18th century, and to discuss the role of the Joule's experiment in establishing the principle of conservation of energy. Right? Those are the main objectives that we want to cover. Right? So there are two main theories that govern the nature of heat. One is the caloric, and the other that you're going to hear about is the kinetic theory. We talked about kinetic Monday to say that kinetic has to do with the motion, movement of particles, and so forth, right? So in this lesson, what we're about to do is to differentiate between caloric and the kinetic theory, because there are two different things when we look at them in a sense. Now, this is sort of what the caloric theory starts out with, right? By the way, we must make mention that the caloric theory of heat is an obsolete theory, right? When we say obsolete, it's like we're negating it. We're not considering it as a as a theory that we use presently, right? That's what we mean. You're writing the objectives. All right, no problem. Sorry about that. Yeah. So what I was just saying a while ago was that the caloric theory of heat is an obsolete theory, which means that we don't use it again. You understand? It's not something that we hold value to. But as science students, we have to understand where heat is coming from. You understand? And to where it is now at. Cool? So back in the days, it was believed that heat was an invisible fluid called caloric. That was what they had the idea to say that heat was um my bad. That heat was an invisible, you know, invisible fluid called caloric, right? Which could combine with matter and raise its temperature. So back in the days, they might say heat was a fluid. So this is the kind of like the main thing that was made mention of when we talk about the caloric theory. Because back in the days, you never probably have a lot of technology to investigate certain things, so you just make certain guesses to say that, all right, I believe that heat is an invisible fluid, you know, like almost coming like air. You can't see air, so they were thinking that heat was invisible, all right? And when it is combined with matter, it causes the temperature to raise. So if I ask you to talk about the caloric theory, this is the kind of like the first statement you should really give off to say that that was how heat was considered to be. It was considered to be an invisible fluid, and we call it caloric. Hence why we say the caloric theory, which could be combined with matter, right, and raise its temperature. We good so far?
Yes, sir.
Mm-hmm. All right. I'm going to next slide. Now, you see, the beautiful thing though, while we are against, well, say not against, but while we don't put a lot of emphasis on the caloric theory, there were arguments that actually made sense. And these are the arguments here, or these are the pointers that were made mention in the time when they were talking about the caloric theory, and these actually make sense. And we're going to read them, and you're going to see that it makes sense. Now, eventually, you're going to find out that whenever objects expand rather when heated, because the increased caloric um, they contain causes them to expand more. This is something that happens in real life when it comes down to heat. When you apply heat to some objects, I think it's most objects, it's going to expand. You understand? And this just shows that there's an increase in terms of the heat inside of it, right? I'm trying to think of an example. Can anybody think of an example where when you apply heat to something, it expands? I think I spoke yesterday about a corn, the corn pebble, and you would have put it in a pot and then you apply heat to it and it would have blown up, right? Sort of expand, right? Um,
Very different class I teach yesterday.
yeah, me know, but Mr. say yesterday we talked about that. Me know it's a different class, but Mr. But I don't know. Think about an example that we could possibly think of, right? That
Sir,
when we
metal.
say it again. I didn't hear you.
Metal.
Yes, yes. Some metals, right? Some metals will expand in terms of their size. Um, you know, and I think I was looking at something else yesterday. You see when you walk on the road sometimes and you see like a crack in between the road, right? That is as a result of the fact that the heat would have caused the surface of the road to expand. You understand? When you're like baking, baking is another example, right? When you're baking like a cake and all of that, one of the reasons why it expands is not only because you have the rising agent inside of it, but it's because of the fact that the heat is causing the thing to expand. And sometimes when you look at the cake, you will see like a break in the cake, for those who bake. So that just shows us that it's the heat that is really causing that to happen. So this concept here is we hold it valuable because it explains things up to this day. Another thing is that the caloric theory was able to say that heat flows from hotter to cooler bodies because caloric properties repel each other. Yes, while we don't know that there's a repelling, but we know that heat flows from hotter to a cooler area, right? Can we agree on that? So if you try to burn a clear plastic pen cap, the plastic starts stretching. Yes, 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 that is true as well. So that is also expanding. Yeah, definitely. All right. So this is another argument that we can hold on to say, that heat actually flows from a hotter region to a cooler region, right? Because when you think about a pot, right? When you light the stove underneath the pot, The center of the pot is going to get hot. That heat is now going to be transferred from the hotter region to the cooler region until there's a point of equilibrium, or we can say equilibrium temperature or thermal equilibrium. Anytime you hear about thermal, we're talking about temperature. If you hear the terminologies that says thermal equilibrium, that just means that you have an even temperature throughout the body of the substance and all of that. Good. Now, I'm going to next slide. Here we have arguments against the caloric theory, right? Now, one of the arguments against it is that it says that when bodies are heated, or when a substance, or when substances are heated, so that they change state from solid to liquid, or from liquid to gas, an increase in caloric cannot be detected. Because what the whole caloric theory seeks to say that, you know, if you apply heat to something, right, it's automatically going to be transferred in a sense, right? But when we're thinking about a change of phase, because this is a change of state or change of phase, we realize that there's not an increase in the caloric that is detected. So this is an argument against the whole aspect of the caloric theory, to say that when bodies are heated, so that they change state from, you know, solid to liquid or liquid to gas, an increase in caloric cannot be detected, right? I know this one kind of sounds a little bit away. It's not so easy to explain or to understand, right? But I think the other one though would be more more easier to understand. So it says that when different materials, right, are given the same amount of heat or caloric, their temperatures rise by different amounts, indicating, right, that they receive different quantities of caloric. Cool. So this is an argument that is going against the caloric theory, right? Because this is because what the caloric theory is really supposed to say is that despite the fact that you have two different types of materials, you should have the same, you know, increase in temperature. There should not be a difference in temperature. But from this, we're seeing that if you heat a piece of metal and a piece of rubber, with the same amount of heat, one of them is going to get the temperature is going to increase in one more than the other, right? And the caloric theory would have been telling us that, you know, if the same amount of heat is applied, then both things, despite the nature of the materials, they should have the same temperature. But that is not the case. You understand? That's not the case. And this is to say that, you know, because remember the caloric theory is speaking about the fact that caloric is a fluid. So if you're giving both substance or both materials the same amount of so-called fluid, then it should really increase the temperature by the same amount because you're giving it the same fluid. But we know that that's not the case, right? So this here just sort of explains an argument against it, to say that when you apply heat to different bodies, right, it what do you call it now? It results in a change in temperature. Now, this number 3 here speaks to the weight of a body, in a sense, where they're saying that, you know, the weight of a body should increase as it is heated, because, right, it should then contain more caloric, right? But however, we know that in real life the weight remains the same. So remember now, we're thinking about caloric as a fluid. So if you're adding more fluid, they're saying that it should increase the weight of the body. But we know that that's not the case, right? So this is just explaining to us that, or the caloric theory is telling us that the weight should increase, but we know in real life that the weight is not going to increase, which just discredit the fact that heat is a fluid. All right. Let me know if you guys are understanding. For the most part, let me know.
Sir, me understand when I understand the part where they say heat a fluid.
You understand that part?
No, sir, I don't understand the part where they must say heat is fluid.
So remember now, that's what they were thinking to say that heat was a fluid. Now look at it now, Rochester. If heat was a fluid, right? It means that the more heat you have, is the more fluid you would have. So right here that says the weight of the body should increase if it is heated. If it is heated, it means that more fluid is added to it, right? So you would expect that the weight would increase, but that's not the case because the weight remains the same. So if you were to apply heat to a dumpling, you understand, and measuring the weight of it afterwards or before, you would see that the heat remains, the weight remains the same. So that just goes to show that heat is not actually a fluid, right? Because the weight did not change. Cool?
So, sir, heat and fluid then, sir. 'Cause if it is a fluid, it would change.
The weight would have increased, exactly. If heat was a fluid, then when you increase the heat in an object, you would expect that the weight of the object would get heavier. You understand? But that's not what is happening. The same thing for number 2, Rochester, and for the other students here. Now, if I am applying the same amount of heat to two different materials, what that is telling me, based on the caloric theory, is that I am giving the same amount of fluid to the materials. And if you're giving the same amount of fluid to the materials, then it should give me the same temperature. But that's not the case. It gives a total different thing. It gives you a difference in temperature. So one is going to increase by a different temperature, and one is going to increase, and one is going to have a different temperature. So there's going to be two different temperatures, so to speak, right? So that also just discredits the fact that heat is a fluid. You understand? It's discrediting it.
Wait, so sir, what that one is basically saying is that if we give it the same amount of caloric, it's supposed to have the same temperature.
Yes, that's precisely what it is supposed to be saying. If we're thinking about it from a caloric standpoint, but we know that that's not what is happening. You understand? Right? So let's next slide and see what next on here. So this guy, um, he was the one who actually, provided evidence to support the claims or the evidence that were against the caloric theory, right? So his name is Count Rumford, right? He was an army officer responsible for boring of cannons during the late 18th century. And I think we understand what is a cannon. If you ever go to Port Royal before, those big old thing when they used to bomb up ships when it was coming into the island, that's what we call a cannon. And he was responsible for boring the actual ball to pretty much, fire the cannon, or fire the thing, fire the ball, to destroy, the ships or whatever it is to fight in the wars. So this is what he realized. He realized that the heat energy transferred when a cannon was being bored was inexhaustible and depend only on the work done in boring the hole. So when he was firing the shot, right, he came to the realization that if you apply more work to bore the hole in the cannon, right, you would expect that more heat energy would be transferred to the cannonball, and of course you'd expect that eventually the cannon would fire to a further distance. You understand? So depending on how much work you apply to it, right? If you apply a little bit of work to it, then it's going to apply less heat energy, right? Let's see if we can look at how the cannon thing works in a sense, just to start to get a field view of what right. Let's hope we can find a short video. So it's a whole lot of things that is going on here, guys. A whole lot of things just to start to explain what is taking place, right? Let me see here. These videos seem to be very long, but I think this one sort of like let's look at this one. Hopefully it is more, a good one.
अस्सलामुअलैकुम डियर स्टूडेंट्स, लेट्स स्टार्ट आवर फिज़िक्स क्लास ऑफ सेकेंड ईयर। आज हम सेकेंड ईयर की फिज़िक्स क्लास का टॉपिक हीट स्टार्ट करेंगे। हीट चैप्टर नंबर 11 जो सेकेंड ईयर क्लास का फर्स्ट चैप्टर है उसे आज हम पढ़ेंगे कर सकते हो और वो हर बॉडी में पाया जाता है।
Man, I can chat some foolish nonsense, man. Like, the man can talk in English, man. I know. Okay, this might not explain completely, but let's just look at how the cannon works in a sense, just to get a better idea.
This is a coastal cannon from England, and this one's more than 300 years old. It weighs 5 tons, and it's made of solid cast iron. Let's go and have a look at the way in which they were made. They started by making a mock cannon out of wood, rope and clay, and then placing it in a bed of sand, special casting sand, which was pressed all around the cannon. It's built up halfway here, and continued to be pressed around the cannon in the second half on another frame. It's a brick frame, as you can see. The brick frames were held together by solid iron bands, and then the whole device was heated in order to harden the casting sand. Now, after this had been done, the two halves were separated, the mock cannon was taken out, and through a small opening in the top here, molten metal was poured in. After that had cooled down and solidified, they broke the thing apart, as you can see here, and they ended up with this, the cannon. Very heavy, made of solid iron. It was so heavy, in fact, that they needed special devices consisting of chains and pulleys and ropes in order to lift the cannon out.
And indeed, they were so heavy, it wasn't easy to move them around, and it certainly wasn't easy to move around cauldrons of molten metal. So sometimes cannon were cast here, in a pit of sand in front of the furnace. And when the iron had melted, the gate was opened, and the metal poured straight into the moulds down there. When it solidified, the solid cannon were once again lifted out by hoists and cranes. Now sometimes in the smaller cannon, the hole for the barrel was cast in the one operation. But for the best cannon, the truest cannon, it had to be drilled out. And that was done after a bit of finishing.
Much of the finishing occurred here with the forge and the tilt hammer. The forge had a charcoal fire which was brought to a very high temperature with bellows. And the object to be treated was heated and then brought out carefully with tongs and placed under the hammer and beaten into shape. In this way, the shape and finish of cannonballs was improved, and also with this hammer, the bands that went around the cannon mould were made. And it was here that the importance of water power becomes evident. That water wheel is driving through a system of cogs, both the tilt.
Alright, so you know that is not kind of giving me what I want mainly, right? And
Basically, so sir, basically what you're saying is that because he was boring the hole in the cannon,
mhm.
the heat was it was supposed to leave right away. So because it didn't leave right away, like it was running away like a fluid, he said that the caloric theory can't be true.
Precisely, right? Because remember now, if you're doing more work, right, and you're seeing that the temperature of the cannon is getting hotter and hotter, then chances are it is not losing fluid. You get me? So that showed that there was no fluid that was being lost. So no fluid had existed in the first place. Let me know if you guys caught that part. I know my internet was a little bit unstable just now, but let me know if you caught that part.
So, so sir, you must say like the cannon would have say full up of fluid, and every time it like release, the fluid should have leave. So after a while, no fluid not supposed to left in the cannon,
Yes, that
but
is
fluid actually left in the
no,
still
no, no,
there, so no fluid no actually there then.
no fluid not in it, you know. But his understanding is that if you are boring the cannon, right, it means that if heat was a fluid, the fluid would have been leaving the cannon. You understand? But based on what he observed, he was observing that the more work you did, right, it's the more heat that was transferred to the cannon. And for that reason, it was clear to say that no fluid was in the cannon in the first place. Because if fluid was inside of it, then you would not expect the cannon to get hotter because you would have been allowing the fluid to escape. You get what I say? It's just like friction, guys. So let's imagine that you are rubbing your hand together, right? That is you doing work. Now, by way of you doing that, right, we're seeing that your hand is going to get hotter. Now, if we were to consider the caloric theory, by you rubbing your hands together, what you'd be essentially doing is pulling out the fluid from inside of your hand if fluid was inside of it, but there's no fluid that is inside of your hand. You see what I say? So this now explains to us to say that depending on the work that you do, right, or that was done to bore the hole in the cannon, right, that work is now translated as heat energy. So remember, we're talking about heat energy and all of that in recent times, or energy on a whole, to say that if you are doing some amount of work, some of the energy is going to be transferred into heat. So in this case, he's boring it, right? And by boring the thing, some amount of heat is going to be transferred to the material. So what it tells us is that there were no fluid inside of the material to be escaped. You understand? Because if the fluid, if you're boring the thing, you would expect that fluid would be running out of it, thus causing the temperature to fall or to lose heat energy and all of that. But that's not what was taking place. I wonder if we.
Oh, sir, I understand, sir. So when he was boring it doing the work, he expected the heat fluid to run out, but no fluid was running out and the metal was getting hotter. So he realized that no fluid was there in the first place.
Precisely so. Right? That's the best we can consider it for now. Let me just check this textbook here to see if it have anything related to that. All right. Give me a second here. All right. Give me a second to just check this book. What time class end today again? 40, 9:40.
I think it's 9:45.
45. Okay. Yeah, I'm trying to just look through a book right here. All right. Let's just read this information. Let me see if I can share the screen again. It might look a little bit blurry, but let's see. This is just talking about the end of the caloric theory. It says during the 18th century, and you guys seen it, right?
Yes, sir.
It says during the 18th century, the most commonly held idea about heat was the caloric theory. This theory used the idea that there was a fluid called caloric that was transferred between objects when heat moves. It says that the caloric would flow from a hotter to a colder one, meaning that the heat would lose some caloric and the colder object gain some. It says objects could only have a limited supply of caloric. Now, Count Rumford noted the heating effect of mechanical work involved in boring holes in cannons. He says, although there was clearly a large amount of heat released, the filings from the cannon had identical properties of the original cannon material. This means that there was no physical substance, the caloric, being transferred. If the cannon was, or if the cannons rather were placed underwater, the mechanical work would also heat the water to boiling point. There seems to be an unlimited supply of heat being transferred. Over the next few years, other scientists, including James Joule, right, developed the idea that heat was a form of internal energy that could be generated by mechanical energy. Joule measures the mechanical energy provided to water and measure the temperature increase. He found that the increase in temperature was proportional to the energy supplied. It's a lot of information, and some of it is not so clear cut as we might imagine, right? But because this is kind of saying something, sort of like, you know, 'cause this information has to be more hard to understand. But at the end of the day, what we must understand is that it was he came to the conclusion that depending on the amount of mechanical work that you do, that is what was